Hey guys, and welcome to another Houdini video tutorial. Today we're going to be taking a look at fracturing within Houdini, and we're going to be using voronoi fracture SOPs to do that today. So without any further ado, let's dive in. So I'm in a fresh Houdini scene, and like always we're going to drop down a geometry node to get started, dive inside and delete out our file node. And we're going to drop in some test geometry, and luckily Houdini has some really nice basic geometry to work with, so let's drop in our trusty pig head. Again, because the procedural nature of Houdini, really this object does not really matter what we're working with, because we can always switch this out with something else further down the line. But let's have a look at how we're going to fracture this particular object. And the more traditional method is what we're going to be looking at today, which is by using a voronoi fracture SOP, which actually asks for three particular arguments. First one is an object to fracture, the points to generate the voronoi cells, and then the optional sign distance field volume for depth sampling. And we only actually need to satisfy the first two arguments to then create a fracture. So let's put in our geometry to fracture, which is our pig head, and let's give it some points. So let's scatter some points onto our mesh and plug that into our voronoi fracture. And we will actually see it cut up all of our mesh. But obviously the amount of cuts that are produced is based on the amount of points that we have here. And it has 1,000, so let's maybe kind of reduce this down to something more manageable to begin with. Let's say about 50 different pieces. And if we visualize those pieces on our voronoi fracture SOP, you can actually see what's particularly happening. Now, just to explain how voronoi is actually being calculated, let's kind of just drop down a grid. Here we go, off to the side. And instead of there already being divisions, let's kind of put our rows and columns down to 2. And we can do the same, so we'll scatter a low amount, so maybe about 10. And drop that into a voronoi fracture again. And let's kind of wire all of these three nodes up, and we'll kind of see what particularly happens. I'll also maybe generate a small sphere, so sphere, and let's take its uniform scale really far down, and let's just do a copy to points, and copy that sphere onto all of our scattered points. And you can see now the location of every single scattered point onto that grid. And what's obvious to note now is that really these scattered points become the centroid for that fractured area. What it's actually trying to do is give as much area to that fractured piece as possible until it meets the 50% way between the next point. And wherever that 50% actually lies becomes this seam here, and then when it finds another point, again 50% between here and here will become the seam. So that's the easiest way to kind of actually visualize what voronoi fracture is actually doing. So let's kind of jump back to our main kind of object, which is over here, and again all of these pieces are being cut up this way because the scattered points are at the center of this this chunk. And another good way of visualizing these pieces is first, ironically, to have a fractured object, we kind of need to assemble them. So let's type that in as well. And what this does is it assigns a name attribute and an inside piece attribute to all of these individual slices, these chunks. And once that is now known, we can then drop down an exploded view and it will take those pieces and split them all up in 3D space, and you can see how your object has been divided up, which is really, really useful. You can also animate this as well, so if you kind of need this kind of as a channel, that's always good fun to work with. But what you will notice is that because we've scattered all of our points on the surface of the pig head, there is no interior detail. There's no chunks being made inside this, and all of these outside chunks kind of take on a diamond shape because it's trying to elongate how much area it can have based on its incoming point. Luckily, there's a really nice way of generating inside data by coming further up in our node network. And let's visualize our pig head again. Here we go. And let's drop down an ISO offset. The rest of these kind of came up because I pressed O for the outliner and I for node shape. There we go. S for shape palette. So let's plug in our head geometry into this ISO offset, and you can kind of see it here. Let me change my display options background to, let's see if we can get back to there. Right, display doesn't seem to be working for me. Generally you can turn this to a dark display, but for whatever reason, maybe because I'm capturing at the same time, it's not allowing me to change that. But you can kind of faintly see there is a fog volume here, and that is what an ISO offset is doing. It's turning it into a fog volume. Let's upper samples and you'll be able to see it a little bit better. So here is a volume representation of our geometry, and the scatter node is very, very clever. It notices volume data and will actually now scatter points. Instead of on the surface of a data, it will scatter based on using that density attribute. So yeah, it's generating by density this time. And now when we go to our assemble and exploded view, you'll see that we now have interior chunks in this particular head shape itself. So really, really cool. It's a really nice way of actually generating data inside our pig mesh itself. So now that you've actually cut this up into a fractured shape, what we can do is now turn it into a rigid body dynamic object. And again, we can do it by manual as well. So let's put our exploded view off to the side. On our assemble node, we actually want to create our packed geometry that we talked about last time, because at the minute this consists of almost 4,000 primitives. So let's create our packed geometry, and that packs everything down to 52 pieces based on, again, our scatter. So we've got 50 here, which is then condensing it down into those individual points. Let's then drop down a dynamics operator network, so a DOP network, and plug in our assemble to our first node. Our dynamics are completely empty when we do it this way instead of using the shelf tools, so we're going to have to populate this ourselves. First, we need an RBD packed object. Let's just type packed, there we go. And we're going to point this, instead of the geometry source of a SOP operator, let's go to first context geometry and visualize it and see that our pig is coming in. We then need to solve it by dropping down a rigid body solver, RBG, there we go, rigid body solver, and it's going to be set to bullet, so that's fine. We can then apply some gravity. So gravity force. And again, when you're working, these forces are set by default and it's set to meters per second, but you don't have to have minus 9.8. You could make a higher gravity or have anti-gravity. It's completely up to you, governed based on how you feel the effect is working. Let's also bring in a ground plane. And Houdini is quite clever in that it doesn't need to actually state that a ground plane is a static object. It actually knows that by default. So all we need to do is merge it in with our rigid body packed pig head. So we're going to plug in the ground plane first, because the merge node says that the left inputs then affect our right inputs. So ground plane will affect our pig rather than the other way around. And let's plug our merge into our output node, and that's kind of what we have. We will then have to maybe move our object up. So before our assemble, I'm just going to drop down a transform node. There we go. And that will allow us to pick it off the ground and rotate this around too. And visualizing our DOPNet is actually bringing in all objects at the minute, but I actually only want to grab our RBD packed object, and it's doing it based on name. So if I copy this node name and paste it into our object here, it's going to pull out only the pig head itself. So that will work really well for us. And if we press Command and up or Control and up, if you're on PC, it'll go back to the first frame, and then press up, it will play through. And we're getting our fractured object. Now, a lot of students get really confused thinking that this is actually staying as a unified whole. These are actually all individual parts, but are falling at the exact same rate. So it is entirely fractured and it is not connected together. And I can prove that by going into our DOPNet, going to an RBD packed object, and setting some initial velocity, for instance angular velocity, for maybe let's say 150. There we go. Some spin in the X direction, and as you can see, usually what you would think is that the entire pig head would rotate until it hits the ground, but there is no glue force actually keeping this pig head together. So as soon as it is given a force, everything shatters apart. So what we can do is in the next part show you how to contain everything together by setting up a bond network for constraints to ensure that all of these pieces stay together. So stay tuned for the next part. We'll get that constraint network actually set up for our object. It's again really simple, and if you need to learn more about it, have a little look at using the shelf tools, but then diving into your node network, and that will start to reveal a lot behind the inner workings of Houdini. So stay tuned for the next part. It's going to be a good one. Okay, thanks guys.